In this lecture, we're going to look at data structures as an overview. What is data structure? A data structure is a way to store and organize data in order to facilitate access and modifications. So really the purpose of a data structure is to allow us to easily access or modify some data, typically combined with some kind of algorithm. And so there are different kinds of data structures. You have static arrays, perhaps the most basic data structure. You have a block of elements allocated contiguously in memory. And then you have what's called dynamic set data structures. And then we have trees. Also, the last one is called graphs. Now, before we move on further, let's look at what's the difference between data structure and ADT and the algorithm. Now, this really is the core of your application. Now, application uses a lot of ADTs to implement its functionality. ADT, as we explained earlier, this is a way to encapsulate or a piece of functionality that operates on some kind of data. You provide an encapsulation of that data through data structures. And data structures can be considered an implementation of ADT, that you use data structure to implement the functionality of an abstract data type. How do you implement it? That's the role of algorithms. And that's the sequence of steps to do some transformation of the data from some kind of input to some kind of output in the form of functions in this particular language. And you have public functions and private functions. Public functions form your public interface. That's what other components of your program can interact with. So that's kind of the gist of the differences between these concepts. Now, first I want to study dynamic sets. Dynamic sets, in contrast to the static arrays, which is static, you cannot, basically add or remove data, essentially. I mean, if you allocate an array of size 100, that's what you get. You get this memory location. You may choose to use a portion of it, but that 100 locations are occupied. So dynamic sets allow you to adjust the size of your set of data dynamically. So each element is an object. You can access an object via a pointer. The object may have a key, is an identifier. It may contain satellite data, which doesn't do much. It just carries along. But as far as the data structure operation is concerned, it doesn't really care what you're carrying around. So the satellite data is kind of innate. That just is there as part of its data structure, part of your object. And it may also contain data that's manipulated by operations. To store a data structure in data types or some other data structures, you have to record certain kind of data information that keeps the structure of data. So that's kind of information you may have to store on the object. So some of the operations are going to modify them. That's part of data structure. And then the keys may be ordered, like natural numbers. You can compare them. You can find the minimum and maximum. So what can you do? The ordered operations on dynamic sets. You may search a particular element identified by this key, K. You may find the minimum. You may want to find a maximum. Or, give me the successor of an element pointed to by X. Or I may want to know the predecessor. Now, successor is just the next element. Predecessor is the previous element. And then you may want to modify the data structure. Say I want to insert a new element at, you know, the element that's to be inserted is identified by this pointer X, or I may want to delete that one. There are different implementations of dynamic sets. Stacks is one of them. So in stacks, the element removed from the set is pre-specified. The element has to be the one that's most recently inserted. So that's kind of called last in, first out, or LIFO. And we also want to call the operations of insert and delete with push and pop, just so that it's easier to communicate. Because consider the example of a stack of plates. Let's say the spring-loaded stack of plates used in the restaurants. You only retrieve the top plate from that stack. If you want to put a new plate on top of it, and again, you only go on the top. So it's like the last plate that goes in is the first one that goes out. So here's an example here. So you have, let's say we implement the stack with an array. The capacity is 7. We have 4 elements there already, and the top is pointing at this position number 4. Then we're going to insert 2 new elements to it. Well, actually, push to it. We push 17, push 3. If you push 17, the top would have been pointed to the 17 or position 5, and then push 3 again. Now the top is at position 6. And then let's say we're going to pop an element from the top. So it was at the position 6. Now after that, top is popped. So the top is changed now, move to the next one, which is 5. So queues is another dynamic set. In queues, the deleted element is the one in the set for the longest time. So it's kind of the opposite of a queue. So this is called the first in, first out, or FIFO. And insert is called in queue. Delete is called DQ. An example of queue in life is a line of customers waiting to get service. The guy at the front of the line or the head of the line is the one that waited the longest. Of course, they're going to get the service first, which is basically DQ'd. And a new customer comes in, is going to get in-queued to the line that goes to the tail. So we'll also remember this, keep these 2 pieces of information in the data structure, the head and tail. Let's say right now, we're also going to use an array of capacity 12 to implement a queue. You have a head right now pointing at a position 7, and the tail is 12. Now the tail is pointing at the position for the next element. If we're going to, in-queue another element, it goes to the position, the slot pointed to by the tail. So now we're going to in-queue a couple elements. We'll in-queue 17. It goes to 12. In that case, where does the tail go? Tail goes to the first, thinking of this as a circle. So we take advantage of the space that's offered by this array. And then if I in-queue another number 3, and it was going to move to position 2. If I in-queue another number 5, and then it will move to position 3. This is what it's at. Now, what about DQ? So let's say we DQ the element that's at the head. So then we just move the head to the next element. That's DQ operation. Now, another dynamic set is called linked lists. Linked lists are data structures where the objects are arranged in a linear order. Looks like this. A list may be singly linked. An example here is doubly linked. You see there's two links from one element to the next and the next back to the other one. May be sorted or unsorted. Those keys are maybe not in a particular order. In this case, is unsorted. Maybe circular or non-circular. You know, you could potentially wrap around your tail. You know, it's connected with the head. Each element of the double linked list is an object with a key, and also we maintain two pointers for the structure. We have one pointer points to the previous element, another pointer points to the next element. And then if we're going to, let's say, insert an element with a key 25 to the list, and we insert it at the head position. So essentially, then we're gonna point the head to this new element and establish the link between this new element and the previous head, like this. You have two links to establish. Okay, what happens if we want delete an element? In this case, let's say we want to delete element with a key number 4. How do we delete? Essentially, you would basically have to reestablish a link from this key 16 with key 1. And they will be connecting with each other, and the 4 is out of the way and deallocated. Trees. So trees are data structures where the objects are arranged in hierarchical data tree structure. Is actually a tree that's upside down, right? The root is at the very top. That's, you know, convention, easy to look at. There's also variants of trees. The trees could be rooted. Here is a rooted tree. You see clearly a root node. It could be unrooted, where there's no clear roots. And then it could be ordered or unordered based on the key values. And here, this presents an example of called a rooted binary tree. A binary tree, basically every node has at most 2 branches. So in here, to maintain the structure, the way to represent it, we maintain 3 pointers. We maintain a pointer to the parent. We maintain a pointer to the left child, another pointer to the right child. And if, like, here's an example, another node. This one does not have a right child, so the right pointer is null. Same thing goes for the left child. And the root node does not have a parent, of course, so that P is null as well. And so this is how, now what if I have more than 2 branches? And we're going to use a different way to represent it. So this is called the left child right sibling representation. Here's an example here. So instead of maintaining pointers to the left child and right child, because now we have more children, right? What do we do? So the left pointer is still going to point to the left child, but the left, but the leftmost child. It's because like here we have 4 children here for this node. And so the left pointer actually points to the leftmost child. And then the right pointer does not point to a right child. There's no more right. There's like too many, right? So this instead will point to the rightmost, the immediate right sibling. If it has more siblings, but it doesn't care, just the one that's adjacent to it. This is with this structure, we can capture the entire tree information, and then you can manipulate the data and operate on this. Graphs. Now, trees are actually a special instance of graphs, just mathematically. But we study graphs a little different, and the algorithms for graphs are a little different from trees. The graphs are data structures where objects are arranged in a graph structure. And then when you see a graph like this, so you see vertices. There's 5 vertices here. and then you have edges between the vertices. And of course, a graph could be coming in many shapes. So it could be directed or undirected. Here, these edges are undirected. You may have also directed. In a way, if you look at the tree, these are actually directed. But anyway, a graph could be cyclic or acyclic. Now here means it doesn't have a circles. Yeah, this has a circle, so it's cyclic. It may have weights on the edges, weighted or unweighted. This is unweighted. Now with this example, how do you encode this information in the data structure? Well, two ways to do it. First way is called adjacency lists. The adjacent list, so first we're going to have an array of the size of the array is the same as the number of the vertices. So I have 5 vertices here, and then I'm going to have an array of a size 5. And then each element of the array represents one vertex. The vertex, let's say we'll look at number 2. And then we need to maintain information about the edges. So we'll look at the adjacent edges. So we have an edge with a 1, an edge with 5, edge with a 4, and 3. So we'll put them up here in a linked list. So this encodes all the information we need about a graph. Another way to do this is called adjacency matrices. So this adjacency matrix, let's still look at number, let's say, well, actually this is first of all, is arranged in a 2-dimensional array. For a 5 vertex graph, we're gonna create a 5 by 5 array or matrix. And then the value of each cell, if I look at the 2 with a 1, 2, 1, between 2 and 1, there's an edge. So that is a value 1. And then 2 and 2 by itself, there's no edge. 2 and 3, an edge. Now what about, let's say, 1 and 4? Well, between 1 and 4, there's no edge, so it's 0. So this is just another way of representing a graph. So let's actually take a look at the libraries. So that what we have just looked at are some of the fundamental data structures at a high level. We're going to study in more details in coming weeks. And this is just a slide on C++ libraries, because libraries, the standard provides out-of-the-box data structures. So these data structures that you see here, that are called the containers. Container, you can think of it as just a collection of values, a collection of elements. Typically, that's what data structure is about. And then if you look at, there's different categories that suggested here. We have sequence containers. The name of the category is not that important. Let's just say, array. Well, these are the kind of the containers where you access the data structure sequentially, or the elements are arranged sequentially. Array, this is the standard array. C++ array is a kind of a wrapper on the C-style array. And vector, it uses the array underneath and then manages the resizing dynamically. And you have a deck, double entity queue. So instead of having, new customer coming to the end of the line, you could also have them cut the line in the very beginning. That's what it kind of means. Forward list is a singly linked list. List is doubly linked list. Associated attack containers, these are the containers where you store a collection of values identified by keys in a sorted manner. So this set is actually sorted set. You also have a sorted map. Map is a collection of key value pairs. You access elements by the key. Those keys are unique, and then if they're not unique, and you use a multi-set or multi-map, and then they could be coming in the unordered fashion. Now there's a cost in maintaining order, so it depends on your particular use case. You want to pick the right one. And then the stack and the queue, they're just an adaptation, because you can implement them easily with the different kinds of data structures. The simplest kind that we just saw was just a simple array as the backend data structure. You could also have the priority queue that, meaning the elements have a priority. When you dequeue, the priority matters. Then the libraries are implemented in a few very popular open source projects. You have a GCC, LLVM, and also Microsoft. They're all open source. So if you're interested in the source code of how these things are implemented, then you can check out the source code from these different projects. GCC and LLVM, they are compilers for C++. If you're on Linux, mostly you're using GCC. On Mac, it's mostly the default is LLVM. If you're on Windows, you're using Microsoft's own version. But if you're using the Linux subsystem on Windows, then of course that's Linux. Another library that I like to mention is called the Boost. Very popular library, has a lot of the functionality implemented that's not part of the standard C++, but over time, some of the features from Boost get standardized. In fact, the Boost committee and the C++ standard committee, they share some members. So, but the Boost has a, a graph library that's not in the standard, so you may want to check that out. So that's pretty much it for a little overview of data structures. Thank you.